I'm going to do two problems today. I'm going to work through at a reasonable pace because you should all have attempted it. The problem I set you as learning at home, homework. And then I'll do a second problem, get as far through that problem as possible. With regard to Wednesday, I saw someone sent an email around saying what's required for us to fill out on that piece of paper that you are going to be handing in on Wednesday for the bridge testing. A couple of sentences. A diagram on itself is not enough, but by all means draw a diagram of your structure and talk what it is, truss. So our bridge is a truss bridge. Our bridge is a combined arch truss bridge. In terms of load paths, well, you talk through the load paths and the structural actions, being, of course, bending, axial, shear, distortion. So you talk that through. So no more than a few sentences. A few sentences should suffice unless you have a very complicated type of bridge. Now, it will be a bit mad because there are so many of you, so I intend on getting here 10 to 15 minutes earlier to start the weighing process going, so we can then run through the testing very quickly. So if you don't have anything before this class and you wish to get your bridge weighed and set up so we can start testing shortly after the time starts, please do so. Okay. So it's all about deflection now. We're talking beam deflection, and I gave you this problem to do. We worked out I think we had drawn the bending moment diagram as an exercise in that and the shear force diagram. Now with this particular problem, there's an internal pin at C. So thus, please. You have to split the system at the pin at C. And when you split it in two halves, as I have drawn here in red, you then have to ask yourself, which half can I start? Where can I start? So the right-hand side does look simpler. However, if you attempt to get your boundary conditions here, if we do consider X to start here when you look at the right-hand side, and X to start here when you look at the left-hand side, over on the right-hand side, you would say, okay, well, when X is equal to 6 metres, that's at point D. Shush, please, I can hear you. The deflection is 0 because that is, of course, a roller support, and Y is, of course, our vertical deflection. However, if you attempt to get your second boundary condition, we can't say that the deflection at C is 0 because that point can move. So therefore, that would tell us we can't start on the right-hand side. We would have to start on the left-hand side, where over here our boundary conditions would be, well, when X is 0, Y is 0, and because there's a second support in there, when X is 6 metres, Y is also 0. So I'll work through this, as I said, at a fairly reasonable pace. If I am going way too fast, slow me down. And we'll see how far we get in the time. I do want to try and get started another problem as well. Okay, so, we've done that bit. Okay, so let's get going. What I'm going to draw now is my free body diagram of the left-hand side with my known reactions now, because that was the first thing we needed to do. Now, when I cut this beam, I'm trying to come up with one equation valid for the entire beam. So when I cut this beam, I'm cutting at a distance x, and that x represents anything from 0 to 7 metres. So I'm not cutting it at 7 metres, I'm not cutting it at 3 metres, I'm cutting it at x metres. And the equation I come up with using singularity functions will be appropriate for all values of x in there. So the first thing we look at when we look at this problem now is to say, I have a discontinuous uniformly distributed load. That means it doesn't run into the cut. So when you make the cut, you have to consider it to be as far right as possible. So you would make sure you encounter all your loads. So because it doesn't run into the cut, we are going to assume it does run into the cut. And because we can't go adding load, we will then be taking the same load away from the bottom. So why are we doing it? We are doing this so we get one equation that is valid for the entire beam. So looking at our system now, we have a distance x, and we have to define this distance in here, because when we take moments at the cut, we want to know what that distance is. Now, we know the UDL load loads up 6 metres of the beam, so this distance in here must be x minus 6 metres. So now we have our free body diagram, it's in equilibrium, and now we come up with our equation, and for that we always take moments at the actual cut. And as I said, this cut can be anywhere from 0 to 7 metres. So taking moments at the cut, I have my moment m. Then I usually move as far left as possible, and I work through my loads. I have my reaction at A, 28.33, times the distance x. Tell me, is that causing clockwise, or should that be plus or minus? Minus, because it's going clockwise. Then I look at my load along the top here, my 10 kilonewtons per metre. So I am assuming the 10 kilonewtons per metre on the top runs over the full length. So my load will therefore be 10x. And when I take moments, because it's a uniformly distributed load, I assume that load is acting in the middle of x metres. So my load is 10x, and my distance will be x on 2. And taking moments at the cut, that's going anti-clockwise, so that's plus. And then I have my reaction force, 41, so that's 41.66. This is a distance x minus 6 from the cut and causes clockwise rotation, so that will be minus. And then I have my final term, which is this load on the bottom, 10 kilonewtons per metre. Now, this load down here, I'll do it in green, is effectively, if I draw an equivalent load up here, I'll make it extend all the way down so I can give it a value. The value of that equivalent load is 10 kilonewtons per metre acting over the distance of x minus 6. And how far is that equivalent point load from the cut? Well, that distance in here is x minus 6 on 2. So again, I'm just using forces times distances, forces times distances. So in my equation now, if I look at the load, it's going clockwise, so it would be minus 10 times x minus 6. And as I mentioned to you last week, whenever you have a number times a distance like that, you can just automatically square it and divide it by 2. Because we always multiply it by a distance that is half of the distance in the loading. Now, all of that equals 0. And why am I calculating my moment equation here? Because we now know we can relate moment to curvature. And who cares about curvature? Well, if we integrate our curvature expression twice, that will give us a value for our deflection. So I have 1, 2, 3, 4 terms. So there is my general expression for my bending moment. So if from that, I can actually use that to draw my bending moment diagram if I wish. And if I did so, I would get, if I attempted to plot it, I would get a bending moment diagram that looked like so. Now these pointy singularity brackets, what are they all about? Just to remind you, these, oops, let me just go to red. What these brackets are all about is they actually turn on and off the number next to them. So if the term in the bracket is negative, oops, I shouldn't say it's negative, if it's equal to, let me get the eraser out. Okay, the term in the bracket is equal to 0 if x is less than a, if it's negative. And otherwise, it's just equal to the bracket if x is greater than a. And what that means is those terms can be switched on and off. So looking at our current problem, if I cut the beam at, say, 3 metres, so if I now draw over here my bending moment diagram, or my free body diagram, cutting at 3 metres here, can you see in there I haven't come across the reaction at B, 41.33. So if we look at our expression here for our moment, because x is less than 3, that term would disappear. So what this allows us to do, and this final term would disappear as well. So the beauty of these equations are you can write an equation for a discontinuous system. So things just appear and disappear depending on whether you have basically cut them at that point. Okay, so we have our expression for our bending moment, and now we know our deflection is equal to the second integral of m on EI. So we have to integrate this expression once, and we get a dy dx term. Now, that dy dx term is actually the slope of the beam at a point, the gradient of the beam. So if I asked you, what is this slope here at A? That slope at A here is dy dx when x is equal to 0. So value for slope is dimensionless, this value here. When you do work it out, you're actually working it out in radians. Okay? So let's continue now. We're going to integrate this once, and this part of it, I know from experience, you can all quite happily do the integration. The thing to remember is we do not expand these singularity brackets out. When we integrate them in their bracketed form. If we attempt to expand them out, then we lose the ability to make them disappear. So, now the important thing here is this constant of integration. We have to allow for this constant of integration when we integrate. So we integrate once, we get slope. Now within that beam ABC, we actually don't know anything about the slope. But when I say we don't know any value of the slope. We don't know where the slope is 0. It's not in the middle of that UDL load because it's not symmetrical. So we can't actually solve for our boundary condition. Remember back here, the two boundary conditions we know in this system are when x is 0, y is 0, when x is 6, y is 6. So we have to keep our constant of integration here, and we're now going to integrate one step further now and come up with an expression for y, which is, of course, our deflection. That's what we want. So doing that now, and I will put these inkings online. We end up getting this expression. Our first constant of integration we multiply by x, and then we have our second constant of integration. So before we can solve for any of the deflections, we have to solve for our constants of integration. And as I said, we do so using known boundary conditions. And those boundary conditions, the first one would be when x is 0, y is 0. So in my equation I would plug in 0 is equal to 0 plus. Now this is where people go wrong. If you look at this bracketed term here, it's x minus 0. And people say, oh, so do you apply the singularity rule there? You always apply the singularity rule. That bracketed term is now negative. So that becomes 0 minus 0 plus, again, x, 0 minus 6 is a negative number, 0 plus, that's c times 0 plus d. So thus, our first constant of integration, d, is equal to 0. So that's an easy one for you. Our second boundary condition, when x is 6, y is 0. So there's always one easy one for simply supported beams and one more difficult one. So this time round, our deflection is 0 again. And it's 0 when x is equal to 6. So now when I get to my second term, I have 6 minus 6, so that's 0. Then I have my third term, 5 on 12. Then my fourth term is 0, and then I have plus 6c. Now, a few people go wrong here. They forget to multiply c by 6, or they forget to divide c by 6 when they calculate c out. So, plugging in anyway, you get a value of minus 79.98. Now, in saying you get that value, what I forgot to mention is what units we are currently working in. I, at the beginning of this problem, decided to work in units of kilonewton and metre. If you look at the EI value we were given, I'm going to flick back now. We were given, oh no, it says in terms of EI, so we're okay here. In the exam, usually you are given an EI value, or a value for E and a value for I. And to make your life difficult, we usually give it to you in units of newtons and millimetres. So it is not hard to convert, but I would do the conversion there. If you come to this point here and go, oh, I've changed my mind, I want to work now in millimetres, this 6 here would become 6,000. So what you think is you can multiply everything by 1,000, but you can't, because some of these numbers here are already a moment, for instance. They may be a moment term, so then you would have to multiply it by 10 to the 6. So don't halfway through decide you want to change units. At the very beginning, decide what you're going to do. No, if you look at our free body diagram here, x is this distance in here. Yeah? Okay, so we now have an expression for y, and I don't want to write it all out again. So what I'm going to do now is just calculate y at the tip. And at the tip, what is x equal to? It's equal to 7 metres. So now, substituting in here, my value of 7, I'm just writing it up here for completeness, but I think you can all see what I'm doing. That will give me a deflection of 66.6 on EI. So just to go over that again, quite often you're given EI in units of Newton millimetres squared. How do I know they're the units of EI? Well, E is in megapascal, Newton per millimetre squared usually, and I, if you've done your class today, you know we'll have units of millimetres to the power of 4. So that gives you newtons millimetres squared. Now to convert Newton millimetres squared to kilonewton metres, well, I say 1 Newton is 1,000th of a kilonewton, and 1 millimetre is 1,000th of a metre, and that's all squared. So the conversion will be that 1 Newton millimetre squared is equal to 10 to the minus 9 kilonewton metre squared. So it's simple enough. Now the other thing to point out here is y is a positive value. So a positive value represents upwards movement. So this point here now, if I now draw what we know so far, well, we can assume that goes down and this pops up here. And that amount of displacement in there is 66.6 on EI. Now, in the question, we're also asked to find the maximum moment under the uniformly distributed load. 3, okay, I've just got to make sure I've got enough pages. So now our next task is to find the maximum deflection under the UDL load. Now some of you are sitting there going, oh, it's at 3 metres. No, it's not. This is not a symmetrical system anymore. So how do we find it? We know that the maximum deflection under the UDL load is somewhere between 0 and 6. So thus, our deflection equation, we can remove all the x minus 6 terms because they're not in our equation. How do we find where a deflection is maximum? What we do is we set the slope dy dx equal to 0. Because at a local maximum, that's where your slope is horizontal. So dy dx is equal to 0. That means it's horizontal. So what we do is we go back, and I'll just flick back now, to, where is our slope equation? One further back here. Our slope equation down here. And we pull out our slope equation and we equate it to 0. Now, as I said, our maximum occurs between 0 and 6. So this second term will disappear, the 41 term, and that final term will disappear. So we'll just now rewrite that equation here with just the relevant terms in there. And this 79.98 was equal to C. So this is a cubic, which of course you could all solve if you had your, whatever you use, Wolfram, Wolfram, Mathematica, MathCAD, whatever, your programmable calculators. You don't have those. So I will be honest with you, in the exam, you won't be set a question where your slope is cubic. You may be set a question where it's a parabola, because you all know how to solve for that. But without any of those programmable things, you would resort to good old trial and error. Do you remember? You ever seen trial and error before? So what you would do is you would substitute in a value of x and say, okay, dy dx here is equal to minus 36.65. So let's now go to x is equal to 2.4. So dy dx now is equal to minus 5.51. So that's good, it's getting smaller. Then I'll try putting in x is equal to 3 metres here. And doing so, dy dx is now equal to plus 2.585. So we know we've now gone past the maximum because we've gone from a negative slope to a positive slope. So you can, as I said, as I have shown you, it comes out pretty quickly at 2.9 metres. Dx dy is equal to 0.102. Now all these values are on EI, and let's say that that is close enough. When you actually look at deflection, if again I draw the deflected shape in here, well, that hardly, I've just scribbled a really fat red line there. But as you can see, near the maximum, the slope is very flat. So even if you're slightly off in your location, you're going to get a very close value of your deflection. So plugging in that value now, if we now plug in the y value when x is equal to 2.9 metres, that gives us a value, this time of minus. Minus meaning it's deflecting downwards. Okay, now I'm just going to get myself an extra overhead here. Okay, another thing you need to know how to do, and you were asked to do in this problem, was you were asked to actually calculate the point of inflection. So what do I mean by that? If I draw my deflected shape so far, and now I'm going to try drawing it with a nicer smooth line, it deflects down. Because there's effectively a 10 kilonewton point load there, it pops up. So I have tension on the bottom here, and I have tension on the top here. So at some point in here, I have a point of inflection. So a point of inflection is where you have zero stresses throughout the cross section. So how the hell do we work that out? Well, we know stress is equal to my on I. So when we have zero cross sections, that is also where our moment equals zero. So a point of inflection, to find the point of inflection, which you may be asked to do, you need to find when your moment equals zero. Now we know our point of inflection is occurring between 0 and 6 metres under that UDR load. So if we go back to our moment equation, my original moment equation looked like this. But we are limiting ourselves to x between 0 and 6. So thus, we're going to set the second term to 0. And our fourth term to 0. So, let me go back to black now. So my moment expression simplifies down to two terms. And thus what we're going to do is we're going to equate that to 0. So taking x out as a common factor, we get that, from which we can conclude Well, it either occurs when x is 0 or when x is equal to 5.66 metres, which fits in. Now, I don't have the bending moment diagram. We had it last week. You can have a look at it, and you'll see in your bending moment diagram, the bending moment passes through 0. So far, so good, everyone? Okay, so now we have, in effect, finished with the light... Yep.
You've got 50 in the bracket.
Oh, 5, thank you. So now we're finished with the left-hand side of the system. And now we can tackle the right-hand side of the system. So looking at our right-hand side now, this is an internal pin, but we'll just treat it as a load, 20 kilonewtons. So we're looking now at this system. So now when I draw my free body diagram, cutting as far right as possible, I get 10, 20, my moment at the cut. That distance is x metres. That was 3 metres, so that distance in here is x minus 3. Now people say, but what about that reaction at D? What about that reaction at D? We can include it, and I'll show it to you, but it makes no difference. I'll show you what I mean. So now let's, before we proceed, what are our boundary conditions now? So at D, can you see we have no displacement? So our boundary conditions now would be when x is equal to 6 metres, y is equal to 0. But when x is equal to 0 metres this time, is y equal to 0? No. Y now is equal to, what did we calculate it to be? It's equal to 66.6 on EI. So we know the value there now. So that's why you have to work from one side to the other side. We couldn't have started here. We didn't have that second boundary condition yet. Okay, so taking moments at the cut, I have m minus 10x plus 20x minus 3. Now, as I said, some people really want to say, well, what about this reaction D? If you want to include that reaction D, we could. We could include it, say, okay, well, it causes anti-clockwise rotation, minus D, x minus 6. But is x ever get to 6? No. So this term here, you see, is always 0, because the term in the bracket's always negative. The effect of it is in the other reactions. Okay, so we have our expression for our moment, which we now equate to EI times our curvature. And based on timing, I will leave you to finish that off. However, what I'll do is I'll give you enough information here. Information. When I integrate once, so I'll just do the first integration. When I integrate once, that first constant of integration I call C, and that second constant of integration I call D. So I will leave you some answers here along the way so you can check it out. So doing this, you should get a D constant of integration equal to 66.69. AC, constant of integration equal to 56. And your final deflection equation, right of the pen, will look like this. So please do try and work this out yourself. Now, the question asked for the maximum deflection in region CD. So, to find the max deflection, once again, we would set the slope equal to 0. And from that, you will find it occurs when x is equal to 3.36. Oops, sorry, no. It occurs when, x is equal to 3.34, yes, metres. And you would get a deflection equal to minus 58.81 on EI. So just putting that finally all together. Goes down here, up. I'm exaggerating dramatically, and down like so. And this maximum deflection here occurs at 2.94 metres and has a value of that. And up here, we calculated our deflection was 66.6 on EI. And then our final maximum deflection here has a value of minus 58. And as I said, there is a wonderful application of why you learned how to integrate. So, pat yourself on the back. Great, I know why I integrated. So, we are going to move on, but I will give you a couple of minutes. I'll put the problem up there so you can have a look at it. It looks like that. As I said, no point doing easy ones. You can do them yourself. It's best we tackle. Let me just see, I've left enough pages for myself too. So sit there and chat, sit there and stretch, sit there and wake up, or sit there and ponder. How the hell would we calculate the deflection at the tip? So I'll give you a couple of minutes. I don't think we'll be able to finish this one, but we'll see. Hopefully I'll get across enough for you to finish it. Okay. Let's look at this. We have a crank beam, a vertical bit and a horizontal bit. Oh my God, what are we going to do? Try and get as many marks as you can. So calculate your reactions. If all else fails, calculate your reactions. So calculating our reactions down here, tell me, what does AY equal? Oh. Someone call out. What's AY equal? Beautiful. What's AX equal? What's AM equal? Yep. 20. So we've got our reactions. Oh my God, what do we do next? Well, why don't we split it into two, my favourite word, free body diagrams. So I'm going to be splitting it into an AB and an BC. So when I split it here, I have 10 up. So in this corner, 10 down, I must have 10 up. And that's 2 metres. So the moment there must be 20. And then you know, when you cut it on one side, if it's 20 one way, you know you must have the moment that's equal and opposite. 20 there. I had an up 10, I have a down 10, and that balances beautifully with my reactions. So my two systems, free body diagrams, are all balanced, all in equilibrium. Nothing is moving in space. Why have I done this? Because now we've split this into two manageable parts again. Admittedly, one is vertical, but you could all turn your heads 90 degrees or just turn your bits of paper 90 degrees and pretend it's horizontal. So let's now look at, oh, bugger. Let's look at section AB. And let's say X is going that way. So tell me, what are my boundary conditions down here for AB? When X is 0, when X is 0, Y is 0. Because this point here is my fixed support. Now this is a fixed support down here. When X is 0, Y is 0, what's my second boundary condition for a cantilever? This in effect is like a cantilever system. No, I don't know anything about the deflection. So someone said when X is 2, yes, when X is 2, what is Y equal to? We don't know. What is dy dx equal to? We don't know. But what do we know about the slope down at our fixed support? 0. So when X is 0, dy dx is equal to 0. So they would be my boundary conditions for my region AB. Now, let's look at my boundary conditions for my region BC. So in BC now, and BC looks like boundary conditions. So in region BC, what are my boundary conditions? This corner is moving, but it's not actually moving downwards very much at all. The amount it moves downwards is the amount the column is squashing, and the column is hardly squashing at all. So we could say this time round, X is that way. So when X is 0, Y is 0. At the tip, when X is 2, we don't know what Y is, we don't know what the slope is anywhere, but if I just say now when X is 0, dy dx is equal to theta, you might say, yeah, what's theta? Well, if you look on my diagram in here, this angle in here is the rotation here, that's theta. And we know when we come to deal with corners, they stay at 90 degrees. So if I am rotating from the vertical here in amount theta, from the horizontal here, I'm rotating amount theta. And what is this theta equal to? Well, when X is equal to 2 metres, dy dx is equal to theta. So once again, I'm going to use the boundary condition from AB to help me deal with BC. So I'll just write that out for you. So step 1 for AB, we are going to calculate the rotation at B. Then step 2 for our section BC, we're going to calculate the deflection at C using the rotation or the slope from AB as a boundary condition. This is pretty full on. I'll admit it's pretty full on. Okay, so we've got our two free body diagrams. When you deal with free body diagrams, it doesn't matter. So now I'm going to step A. I'm going to look at my boundary condition, my free body diagram AB. So looking at AB, we said there was a 10 down, which causes no deflection. And we said there was a moment here of 20 kilonewton meters. Now that still looks damn ugly. So what I'm going to do is I'm going to rotate AB to make it horizontal. Because for some reason we can just deal so much better with a horizontal beam. So look, here's my problem. So my reactions here are 20. There was a compression force of 10. There was a reaction force here of 10. So for my free body diagram, what do? I cut the beam as far left as possible. And I cut it a distance x. I draw my unknown moment. I have a moment here of 20 and an axial force here of 10. So for those of you that are still with me, and I know there's a lot of you out there, take moments at the cut, even if you're only with me in your head. Imagine what that bend-in moment, that expression will look like. It's the easiest one you could possibly get. I have m plus 20 equals 0. Now, last week I said whenever we have a moment, we should multiply it by distance. And if I did multiply it by distance, distance to the power of 0. If I did multiply that moment by x to the power of 0, can you see there's no singularity bracket there? So that term is always on. It's 20. So if you forget to put that distance in, you're okay. If we had a moment applied anywhere else, you would be in trouble. Okay, so we have an expression for our moment. How are we doing for time? So our expression for our moment is minus 20. I think I'll have to set you some more work in at home. You will integrate that once, only once, because what are we after? The slope. So let me just do that far now. Just give me another minute. So we integrate it once, EI dy dx, and we get minus 20x plus c. And we don't need to go any further than that in terms of integrating, because all we're interested in is the slope. Now, once you have that value of slope, you can then move on to your BC area region. and then use that as a boundary condition. What I will do in my own time is I will finish the inkings for this problem off, so then when you download it, you'll have all the workings there. Okay, I'll see you all next Wednesday, roaring and ready. Please, final reminder, don't make a chunky bridge. And final hint, after you make it, measure it to make sure it's going to fit the rig. So you don't come up here and squash it in and then all your bits of newspaper buckle. See you all next Wednesday.
Semester test.
Yes. Oh, and the other thing is there's a mid-semester test next week in the tutes. I will send an email to you all. You have the schedule, you know. It's worth 10%. I'll send an email telling you what it's on. But it's on everything up to this week, including this week.